In this video, we will be discussing the topic of how to round off digits. Well, sometimes when we are doing measurements, we get numerical values that contain a lot of digits. This can happen because of the precision of the measuring instrument or when we are doing arithmetic operations with the numerical values. So while it is true that more digits just simply means more precision, but it can also hinder the degree of precision of the measuring instruments when we are trying to calculate the values or using different instruments of varying precision. So in order to achieve the required significant figures, we need to round off the values. So the purpose of rounding off digits is keep the value to keep the value simple as possible. And okay, just wait a moment. Is it is stuttering? I have no idea. Okay, okay. So the sorry for the inconvenience. So the purpose of rounding off digits is to keep the value as simple as possible, to make the value close to its original value, and to eliminate any excessive values that does not match with the precision of the measuring instrument. So here we have our later value here, 7.31417, which rounds off, if we round off the digits, it becomes 7.31. So it just depends on the required how much significant figures we are required to have. So here we need to have only three significant figures, so we have to round off the this value into only three significant figures. So moving on, before we go any further, I want you to understand the chain analogy, as it will be very helpful when trying to round off digits. So as you can see, we have a chain that is made up of seven links or hooks, you can call it. Now, if you look closely here, you can see that the third link here, I'm sorry, this is the second link here. Here, this if you look at this link or hook, you can say, I'm just gonna call it the link. If you look at this link, this link looks a little bit thinner than the rest of them, because hence it makes it the weakest link. Now let's say, what happens when we try to apply force on both ends in the opposite direction? Well, obviously the chain will break, but we know it for certain that it will break from this link because it's the weakest of them all. So therefore we can say that, as I have written it down here, a chain is only as strong as its weakest link. So basically, which means that no matter how strong a chain is, it will break from the weakest link, regardless if the other links are stronger or not. Um, s- um I'm sorry, it's stronger or not. Just even if the links are stronger, it will break from its weakest link. Mm. Now, keeping this concept in mind, we can easily apply the same analogy when we are trying to measure something, which is, in measurements, we can say the same for the when we are trying to measure something, that a calculation is only as precise as its least precise measurement. It doesn't matter how much precise value that you got when doing the calculations, which are just theoretical in nature. It will always depend on the measuring instruments and on the least precise measurement. So let's look at the examples to further solidify the concepts here. Here we have example one here. Here we have a simple example of calculating the calculating the area of our rectangle here, we have used a measuring instrument to measure the length and width of the rectangle, which is measured as 3.79 meter and 2.51 meter respectively, both having three significant figures here, 3.79 and 2.51, both having three significant figures, which also has the instrument precision of 0.01 meters. Now, as we already know that the formula for calculating the area of the rectangle is area equals, which is, let me just write it down here, which is area equals length times width. Simple. This is the a formula for calculating area. So inserting all the values here, after inserting the values into the equation, then multiplying, we get the value result as 9.5129 here equals 9.5129. I'm sorry, I forgot to include the unit here, meter. Now looking at the final value, we can actually see that there are five significant figures here. There are five significant figures instead of three. Here we can see that we have three here, three significant figures, but after multiplying, we get five significant figures here. Five SF significant figures here. So the question that arises, how do we know the number of required significant figures to round off? While looking at the first value, it indicates looking at the value, looking at the final result here, looking at the final value here, we can indicate that the final result is somehow more precise than the measured values. Now, applying the analogy, we can say that a calculated value cannot be more precise than the measured value. Therefore, we can comfortably say that the final value that we got should have the same amount of significant figures as the measured values, which is 3 having instead of 5. Hence, the final result here will be rounded off from 9.5129 meters to 9.51 meters, which has three significant figures instead of five. So from this example, we can conclude that the final calculated value must have the same precision significant figures as the measuring instrument. So moving on to the next example, which is the same by the way as this one, but it will come with a little good twist to further solidify your understanding. In the second example, we are trying to calculate the total width of the coins if the coins were to stacked up together. Here, the width of the coins are measured by instruments of varying precision. Basically, we have measured the width of the individual coin with different instruments that have different precisions and which are given as, here we can say that coin 1 is 1.7 millimeter, coin 2 2.19 millimeter, third one is 1.93 millimeter, fourth one is 1.561 millimeter, and the last one, fifth one, is 2.0 millimeter. So let's add up all the values. We get the final result as 9.381 millimeter. Now looking at the file and now looking at the um, now looking at all these values, we as we know that a calculated value must have the same precision as the measuring instrument. But in this case we are using values, different different instruments that have different precisions. So in this case, we will round off the resulting value to the instrument having the least precision. Now looking at the 5 coins, we can say, now looking at these 5 coins, we can say that 1.7, that the first coin, and the last fifth coin had both have the least precise values, having only two significant figures. So we will round off the calculator value to only two significant figures, and the final result will be, which will be 9.381 millimeter to 9.4 millimeter. Now you may have noticed that instead of writing 9.3 millimeter, I have written 9.4 millimeter instead. This is because of the rules that we have to follow while rounding off the digits, which we will discuss in the next slide. Now, firstly, we will look at the right side of the slide here. We have the value as 1.2914 here. So 1.29 is boxed in red color, just simply indicating the number of required significant figures. And just a heads up for you guys, um, in now from here on, all the examples will have only three required significant figures. So moving on, the number one here, the digit number one is boxed in blue color, which is simply a digit after that comes right after the required significant figures. The whole rounding off method is based on the digit that comes right after the required significant figures, which is basically this digit rounded enclosed in the blue box here, which may and this may affect any change in the last significant figures. First we will look at this figure here that comes right after this required significant figures, and from this can affect a change into the required significant figures. So this, with respect to this blue box which contains a known digit, we will divide the rounding off method into three categories, which is digits less than 5, digits that are greater than 5, and digit equal to 5, which is basically 5 here. Now moving on with the first one here, which is digits that are less than 5. So starting off with the digits that are less than 5, which simply goes like, if the digits after the required significant figures that is indicated by the blue underline is less than 5, then there is no change in the last required significant figure, which is indicated by the red underline. So here we can see, in this case we have the given value as 7.14395. Since we need only three significant figures, therefore we will neglect all the other values and we will have 7.14 here. But we also need to check the digit that comes after the required significant figures. So in this case, the digit is 3, which is basically less than 5. So there will be no change into the last significant figure here. So we will have no change here, and the final value will be as it is, which will be 7.14. So moving on with the second category, we have the digits that are greater than 5. So as for the digits that are greater than 5, we can say that if the first digit that comes right after the required significant figure, which is greater than 5, we will add plus 1 into the last significant figure. Now looking at the slide, we have the value given as 3.14725. Since the required significant figures are 3 here, we will have 3.14. We will have the 3.14 as required significant figures. But looking at the digits, right after it, we have the digit 7, which is obviously greater than 5. Therefore, we will add plus 1 into the last required significant figure. So we will add plus 1 add one digit to the digit 4, and we will have the final value as 3.15. Now, moving on with the digit equal to 5, there is a bit of a twist here, so let's go on with it. So the digits which is equal to 5, before this the rounding off depended upon the digit that came right after this significant figure. In this case, it will depend upon the even and odd nature of the last required significant figure. So there are two conditions for it, if for it, which we will discuss in the next slide here. So in this slide, we can see that we have the value given as 8.32521. We will take out the required significant figures as obviously given by the right underline 8.32, and now we will look at the digits that come after the required significant figures, which is 5. So basically we will now check the last significant figure, required significant figures, and determine if it's even or odd. So here we have 2 here, which is basically even here. So we will have no change into the last significant figure here. So the value will be as it is, 8.32 here. Moving on with the final slide here, we have an odd number. So we have the value 8.33521. If here we already know that 5 is given, so we will check whether the last required significant figure is even or odd. So in this case we have number 3, which is basically odd. So we will add +1 into this digit, so we will have the final value as 8.34. So basically saying if it's an even, then it will have no change into the last significant figure, and even if it's odd, then we will add +1 into the last significant figure. And yeah, we have reached the conclusion here. This lecture was a bit different because I have written a script for it, and while I was writing the script, I realized that this video will easily take more than 20 minutes. So the reason that I have written the script for it, because it will make me less confused, plus it will eliminate my stuttering, and on top of all this, it will force me to focus on the topic instead of just derailing off the topic. So I hope you have enjoyed this video and found it helpful. So if you did, then please don't forget to like this video and subscribe to my channel for more future educational videos. If you have any questions regarding this video, then feel free to comment and I will try to answer your questions. Once again, thank you, and I'll see you in the next video. Take care and have a great day.